Okay, hello everyone to our online seminar on interval methods in control engineering. And it's my great pleasure to have with us today Matthias Faes, who is working at the Technical University of Dortmund in Germany, and he's heading the chair for reliability engineering. And yeah, I think he's very well known for his work on uncertainty quantification in different fields. And yeah, we're now looking forward to your presentation on efficient numerical methods to deal with interval uncertainties. And Matthias, the floor is yours.
Thank you very much, Andreas, for this nice introduction. I will share my slides now.
Yeah,
Just give me a small, this should
yeah,
be
that's
visible now.
perfect.
Okay. First shot, okay. I will just hide this panel now. No, that's the wrong panel because I want to see still. That one should be going. Okie dokie. No, almost there. Sorry. It's classic I mean, half of the talk is always setting up Zoom, right? Um, okay, so almost, yeah, now I'm there. Good. Hello, everybody. I hope the weather is so nice in all places where you are listening to this talk. So many thanks, Andreas, for inviting me to have this chat with you today. I know it's interval. So I know this community is a lot about intervals and control engineering. I come from a bit of a different background. I'm a mechanical engineer, and I originally started with intervals and then moved a bit towards more general imprecise probabilities. Now, the interesting thing that I still find there is that underlying is a lot of interval analysis still. So I try to combine a bit of all worlds, what we are doing in this presentation for today. So that's a bit about me. I'm from Belgium. That's the funny accent you hear. I made my PhD postdoc at KU Leuven and then moved to Hanover to the group of Michael Beer as a Humboldt Fellow. After which I then started at TU Dortmund to found the chair for reliability engineering. Yeah, that's enough about me. So what do we do with reliability engineering, intervals, imprecise probabilities, and so forth? So what we do is we try to use numerical models, solving PDEs essentially. Um, we try to use them for designing, optimizing structures in such a way that we have, how to say, reliable, robust, trustworthy designs. Um, so you see some very nice gear model, very fancy colors. That's not, of course, what we are after. We want to make sure that this gearbox runs for a predetermined number of kilometers without failing. When I say model, I feel like I want to need to make this precise. What I mean with a computational model, namely, okay, this is showing very weird stuff again. Sorry for the interruption. Voila. So when I talk about engineering models, I talk very precisely about a computational model consisting of mathematical descriptions of the physics, meaning differential equations that describe how our model structure component system reacts to a certain loading. Of course, as you are also all familiar or aware, we cannot just solve these PDEs directly using our computers. So we need to have discretization techniques that transform these PDE sets into algebraic formulations, finite element methods, but also finite different, finite volume methods. And we need algorithms, of course, to solve these equations. Now, to make another viewpoint, we can look at it like that. So suppose we are just put the hat on of a civil engineer. We have a building that we want to design against an earthquake. So we have a model that represents how the earth accelerates when this earthquake comes by. We pass this as an input to a finite element model that predicts how our bridge starts vibrating. And when our bridge is vibrating, we look, for instance, at how the distance of the angle or the displacement of two columns moves with respect to each other. That allows us to design to say there is a threshold. If we stay under 0.01, for instance, in this case, this is normalized response, of course, we are safe. If we go above, we are failed. So in this context, you can say, oops, our bridge will here, we come outside of the safe domain, our bridge will collapse. I don't know if you see my mouse pointer, by the way. Um,
Yep, that's working perfectly.
okay, perfect. And so here we say it's failed, so we can make some changes to our design, make sure that all this response stays within the bounds. That all sounds maybe too good to be true. And the reason why it sounds to be good to be true is that it is too good to be true, because of course we don't have deterministic models for loads. We have stochastic loads. So an earthquake, you cannot predict precisely how that displacement or ground acceleration profile will look like. We need stochastic models there. When we model our bridges, we are not really sure about everything. So we traditionally in engineering, we are educated to use safety factors. That's one way to deal with it. The more concurrent trends go towards actually quantifying the uncertainties in there as well. The issue is now, of course, if you combine the uncertainty here, the uncertainty there, we get a stochastic response. So we cannot talk about anymore, is my structure failed or safe, but what is the probability that my structure is failed or safe? So uh, I guess I'm starting a bit too general here, but I felt like I wanted to start slow because I didn't really know who would be in the audience and so on. So if we start with probabilistic analysis, we have a Gaussian loading, for instance. We have a limit state function. Remember the threshold line that I drew. And that limit state function separates our uncertain domain or uncertainty domain at least, because we are quite sure at this point still about our uncertainty domain, in a safe domain and in a failure domain. And essentially, if we want to know now the probability that our structure will fail, we integrate this probability density function over the failure domain, and we have a measure for that probability. Any realization of my uncertain variables here will cause some response that crosses the bounds, essentially. Of interest, very often in our work, if we are doing dynamics at least, is first excursion probability. So we want to know the probability that some response extends the bounds. In other words, the probability that this earthquake will, over a predefined fail domain, collapse our bridge. So far, so good. So we have a model for our stochastic process, for instance, a power spectral density function. We have a marginal distribution. We can apply this kind of stochastic models to our bridge and repeat this a lot of times to quantify our failure probability. This thing is standing in the way again, so I have to put it somewhere else. Whoops. Okay, that's a very short crash course in reliability-based design. So we are quantifying failure probabilities essentially, given the fact that we assume that we know our uncertainties. Now, the issue with that assumption is, of course, we are dealing with real data. We are dealing with the fact that we cannot measure as much as we want. So we have always, in essence, we need to have this joint distribution function fz to estimate our failure probabilities accurately. Now, this estimation is, of course, complicated, and complicated in the sense that we have only imprecise measurements. And so we have measurement devices that don't give a very precise measurement or don't have enough resolution to give the measurement resolution we would want to have. We have small sample set sizes because we cannot just test everything all the time at any point, for the simple reason that there's never enough time and never enough money to do so. We can have incomplete expert elicitations. We can have changing environmental conditions. We can have vague information, dubious information. The point I want to make here is there is always uncertainty about the measurements that we use to fit our uncertainty. So we are turning a bit in a circle in a way. Another way to look at this is what I wrote here. So we are actually observing conditional probabilities under unclear conditions. There are some, so if you look at it from Bayesian theory, this failure probability, of course, is a conditional failure probability, namely it's conditional on the assumption that we have our models right. Okay, or it's conditional on the assumption of certain parameter values for our probabilistic models. What does that mean in practice? Because this is all, of course, you say, of course, Matthias, that's all true, but what does it mean if I'm designing a structure? How does this affect me? So let's look at a very precise case study. And so I showed this bridge with an earthquake. I don't know if some of you are active in the domain of earthquake engineering. In that case, I'm sorry for the simplifications I make in this introductory example, but it's to prove a point. So typically, earthquakes are modeled using power spectra such as Clough-Penzian spectrum. So this Clough-Penzian spectrum tells us how is the energy of an earthquake distributed along several frequencies in the frequency domain. Okay. Now you see It's quite an elaborate equation. It's not so difficult, but there's quite a lot of terms, and those terms they come from tables. Okay, so if you take a book and you look at Clough-Penzian spectrum, it will tell you for omega G, you put for a firm soil 8 times pi, for a soft soil 2.4 times pi, for instance, that you do for all those parameters. You get your power spectral density, you can generate random field stochastic process realizations, and they look like this. Now, the issue is if you look at the difference between firm, medium, and soft, so these are the different power spectral densities, these are the different responses. And you can already see that this yellow, this firm soil, gives rise to higher accelerations of the ground. Now you can still think, yeah, but is it all so bad if I make a wrong decision here? I can maybe run it twice. I can run it maybe for all things and take the bounce. Those of you, I guess I'm preaching to the choir if with what I'm saying now. If you do this, you're already doing some kind of implicit engineering interval analysis. Um, of course, it's a very rough one because you don't know what's happening inside of those bounds. Now, if you just would do this, take medium, firm and medium soil and run a proper interval analysis over this kind of reliability problem, you end up with failure probability bounds, which are 1 to the power of minus 1 as an lower upper bound, and 1 to the power of minus 7 as a lower bound. So that means anything between 1 out of 10 buildings will fail, and 1 out of 10 million buildings will fail, given that earthquake. That's not that's a real problem. So that's something that's a bit too much ignored, but that's something we need to take into account, essentially. I'm still not getting used to online lecturing without seeing people's faces. So in case anything I say is problematic or not clear or so, just feel free to interrupt me, of course, because usually when I'm teaching or lecturing, I try to read from people's faces if what I'm saying makes sense. So please feel free to interrupt me. So what I'm actually was trying to say here in this case, in this problem is we have our models to estimate reliabilities, but we don't actually have the input to fully trust them. So rather than looking at one specific probabilistic model, we should actually be looking at sets of models, sets of probabilistic models in the sense that they represent all possible probabilistic models that are corresponding to the state of knowledge that we have. Okay, that means we have here a set of marginal distributions. For instance, we have done 5 measurements of the soil. We have some idea of how it might look like. Instead of saying now we use this kind of precise distribution and trust this one to the very end of the road, we say, let's take the set. Let's see what happens. The same we do with our correlation models or power spectral density models, for instance, coming from estimating different kinds of parameters in this Clough-Penzian spectrum. We then apply all these models to our structure again, and we end up with bounds on our uncertainty. Not on our uncertainty, rather on our failure probability. Now, are those bounds? Okay, you can write the equation down like this, but that's what I meant before. Actually, we only have conditional probabilities in here for a failure probability. So if we want to find the worst and best case behavior, we have to look for those parameters inside our probabilistic models that give us worst and best case results. Now, those bounds, you can argue, Matthias, you just replace the problem. You replace the problem by that it was in the first place, find me the correct probabilistic model. Now you replaced it with give me the correct bounds on my probabilistic model. And I have to say, yes, you are right. But we are not really interested in those exact bounds in this engineering case. I know there is a whole lot of very excellent work being done in the interval community about finding exact bounds. In this particular case, I say we are more interested in the, let's say, area order of magnitude. Why do I say that? Because suppose you have this example with the Clough-Penzian spectrum. You run this imprecise probabilistic analysis, and the result is the one I showed, 1 to the power of minus 10, 1 to the power of minus 7. Essentially, all you know is you know nothing. Okay, you cannot make any decision in there. You can, of course, say, I now design my full structure for the upper bound of the failure probability, but you might end up over designing everything. So what that analysis tells you is go back to the lab, collect more data, improve your estimations, improve your assumptions, make a more precise analysis. On the other hand, if you come back with the results and they say it's 1.3, 10 to the power of minus 7, 1.5, 10 to the power of minus 7 as bounds, you can say, okay, my knowledge is imperfect, but it seems that it doesn't really matter for what I want to achieve with this particular analysis. Can I trust these data in general? No. Can I trust them for this particular analysis? Yes. Which does not mean, of course, that you can just, as we say in Dutch, throw your hat at the interval analysis that underlies this. Of course, the calculation scheme itself should be precise. Sorry. What I'm saying is the data are imprecise, and that's okay. If it doesn't make sense, I'm happy to elaborate this a bit more later during the discussion. But what I want to say actually with my long introduction is that even though we are doing imprecise probabilities, underneath is lying an interval problem because we are looking uh, at an interval for input parameters, hyperparameters, sorry, which gives rise to a set of distributions which capture the state of knowledge we have. This gives then a set of output distributions which each have their own probability of failure, which gives rise to an interval of failure probabilities. So actually what we have is we have an interval problem where every realization of the interval triggers a reliability analysis. Um, that's the problem we are looking at. Okay, so this is really expensive. As you can imagine, so those of you who are aware of probabilistic reliability methods, single one of those can already cost you a few thousands up to a few millions of model evaluations if you're not careful. Now I'm coming and tell you, well, you know what, you should build an optimization around it. Um, and that's where our research is actually focused on largely is on how to bring down this computational cost. I will skip, I thought maybe I skip this, but I actually won't skip it because I know I come from an interval background myself. So for me, an interval means I have an upper bound, I have a lower bound, and in between, I know nothing. Okay, so there is no, it's a segment of the real line, end of the story. Now, for analysis reasons, I'm not talking about the theoretic or the philosophical implications of what I will say now, but purely from an analysis standpoint, in the engineering community, you see it happen a lot that people say interval. That sounds like a uniform distribution to me. So I will just represent it as a uniform distribution. That's of course not correct. I don't think I'm saying anything shocking if I say that's a bad idea. And one way I found very elegant to explain in this context is let's look at it as a p-box. So a p-box is a set of distributions. If you have an interval, you can also say, and again, I would be very happy to discuss this later. If you say I have no knowledge about the points inside my interval, it is the same as saying, or is it equivalent at least to saying it could belong to any potential distribution that has a support that is my interval. That means you have some kind of p-box where an infinite number of distributions lie in. And why do I show this? I have to show this more in engineering contexts, I guess, is of course this uniform distribution is just one out of infinitely many distributions that might be living inside your interval. Of course, it could be just a Dirac function. Could as well be. But that's a way to show it. Again, I would be very happy to discuss this afterwards, this idea. So how do we perform interval analysis? I think I can skip this slide in this community. Another thing I see happen a lot, I don't know if you see it happen in your communities as well, is that people start sampling from intervals. And so you could just say, okay, I have here my bounds on my parameters. Why not generate a set of samples according to your uniform distribution, propagate those and calculate min and max over those, and then I will surely have a good idea. That's what I quickly wanted to show with these slides, that it's a horrible idea, actually. And so you get essentially the Monte Carlo simulation rate of convergence. So I saw in the description of the lectures that you are especially looking for people doing optimization. Before I go into what we do with optimization, I first wanted to talk a little bit about how we could potentially propagate intervals with sampling. Now, before you throw me out of this meeting immediately, it's a small trick we do, and it's more like it was more of a fun side project of one of my PhD students than anything else, but it really works very well. So the idea is the following. We have our interval. Oi, I don't know why there are balloons flying, so I will keep my hands down. We have our interval, and what we do is we fit a Cauchy distribution to it. So we take the center point, we take the width, and this is an original idea from Vladik Krinovic, who did this a while ago, and we took this idea and continued it further in the sense that we applied it using a multi-level quasi-Monte Carlo scheme to make this highly efficient. So we take the interval, Cauchy distribution on top, mean range, or midpoint range at least, and then we build this multi-level Monte Carlo model on top where we iteratively, adaptively select samples according to multiple levels of this Monte Carlo estimator. Because of course, if you just do sampling, you again just have a sampling efficiency of a Monte Carlo, so we wanted to make this more efficient. I will skip on the details in the view of time, but you can check the details in the paper that's below. So essentially, what we do is we have this multi-level estimator. Where are my slides? Okay, I explained most of this, I guess. I lost my thread a little bit. I made me lose my thread a little bit. Okay, here I want to say something still. So we have our hierarchy of models, so to say. We start with a rough grid, where the idea is this is very cheap, so we can afford to simulate a lot of samples on this one. And the more fine you make your grid, the more precise your evaluation becomes, but the less samples you can afford. And so the main question is, how do I distribute the samples I take to estimate this Cauchy distribution again at the output, which we can convert back into an interval in case the model is linear. I forgot to explain that one. I'm sorry, I'm a bit chaotic sometimes. So we have our Cauchy distribution, we sample it from it, and we build a Cauchy distribution at the response again. Now, the main trick we pull here is, of course, that a linear combination of Cauchy distribution stays Cauchy distributed. And so that means that we can just estimate a Cauchy distribution again from the samples we generate, and we know that is an interval again with the proper rescaling and so on. Now, the trick is, of course, we do this with a multi-level strategy where we choose how many levels we want to sample from based on the bias that we introduce. And so you can imagine this model will be fast, but will have a biased prediction because we have not a converged finite element solver. And the number of samples we generate with the variance constraint. And so more samples will reduce the variance. Now, of course, as I said, we can generate a whole lot of samples here, and that's the idea. So we generate a whole lot of biased samples and then use this correction term with a few high fidelity runs to correct this bias, essentially. And what I wanted to show is if we compare this, for instance, with a vertex analysis, works perfectly for monotonic models, but scales quite bad with the number of inputs. And what we see with this interval multi-level quasi-Monte Carlo sample is that you stay actually constant. So this is not affected by the curse of dimensionality anymore, but only works for linear models. As I said, it was building on an existing idea. It was a bit of fun, and he had a nice paper published with it. Okay. A bigger piece of work we do in our group is related to Bayesian active learning schemes. And that's what I wanted to talk a little bit more about because I think they are pretty powerful. And I would also like to get some input from this community on what we are doing in there. And so the idea is the following. We have a model, and that I explained maps from an input to an output, and we want to estimate whether that output exceeds a boundary or not. What do we do here is we start with generating a data set D, having a number of observations of this input. So we run, for instance, our finite element model 20 times and build a data set. Based on this data set, we build a Gaussian process regression model and compute the maxima of the expected improvement and the minima of the expected improvement for new training points. Okay, so what we do is we look where can I improve my estimator of my maximum of my interval, where can I optimize the estimator of my minimum of my interval, and try to learn uh, based on a few criteria. Again, I refer to this paper because I try to keep the math as much as possible out of this presentation. Based on a few criteria, we try to balance the computation cost between finding the bounds as optimally as possible and using as few samples as we potentially can. That's a bit vague, but there are some learning criteria. I guess most of you are familiar with this field of active learning kind of training for reliability methods. What this is an active learning method for interval analysis based on some Bayesian interpretation. And so what do I mean with the Bayesian interpretation is we have a Gaussian process, and then we retrain this Gaussian process in a Bayesian way. And so new data becomes available, and we apply our Bayesian framework to retrain the Gaussian process model. Just to show that it works, so we have this tower here, which is the numerical model. We have a bunch of interval inputs, and we want to know the displacement of a tip here of this tower. And normally, of course, the first thing you could try, or the go-to method to use in this context would be to use an optimization algorithm, right? So you could hit it with a particle swarm optimizer, which would cost you, roughly speaking, 6,000 model calls to get those bounds. The method we designed does the same in 70 full model evaluations. Why? Because we are, of course, leveraging on this Gaussian process model to do the exploration of the solution manifold, if you want, and use very select full model runs to correct if we think that a potential point is close to a boundary, if that somehow intuitively makes sense. And by doing that, you can really reduce your calculation cost with orders of magnitude. So 2 orders of magnitude to be precise. We applied this method also in other contexts, like full reliability analysis, but also imprecise probability analysis. It's an ongoing piece of work, and I didn't update the slides, update the citations on this slide, to be honest. And so we also this year still published a few interesting works in this context. For instance, aiming at predicting full response distributions. And so not only scalars or excursion probabilities anymore, but we can predict essentially the full response distribution. Okay. The final topic I wanted to chat with you about is what we did very recently on combining interval analysis to model geometric uncertainties. That's quite an open topic for us, is how to effectively model geometric uncertainties. I'm not talking about plate thicknesses. I'm not talking about just the pure parametric kind of geometric uncertainty like hole diameters, but I mean really shape uncertainty. The motivation could be, for instance, if you have very small intervals, you could be looking at how to model realizations of a tolerance field. On a larger scale, it could be related to any kind of manufacturing process, wear process, anything where you are not sure about how your geometry evolves, for instance, in time or within batches or whatever reason. This paper has been accepted, by the way, 2 or 3 weeks ago. So, another good example of interval uncertainty in geometry can be if you look at the design process. For instance, if you are in a very early design stage, you don't really know yet what the other people working on subcomponents of the same system are doing. So you don't know what the exact bounds or what the exact realization will be of the geometry. So what you might want to do is maximize your flexibility and work with an interval valued geometry, such that you can later fit it into some kind of design. Um, that means, however, that you have to be able to deal with multiple realizations of your geometry. That's not always so easy. If you do it with a finite element model, for instance, it would mean you have to remesh. If you now want to simulate with this and with that, remeshing introduces non-differentiability in your objective function, so you cannot already use gradient-based optimization anymore. So finite elements are a bit tricky in this context to be using together with geometric uncertainty because, of course, of the remeshing, which creates issues if you do this in an interval sense to find your bounds effectively. Of course, you can say I run a semi-heuristic or a swarm-based optimizer. Um, Still, you will be generating a whole lot of neural meshes, and meshing might be expensive depending on the model you're looking at. So the idea what we had, or at least what we had, is to work with isogeometrical analysis. So what the core idea, is it in my slides? No, it's not in my slides, so I have to explain it like this. The core idea is to use the same NURBS, so the same B-splines that are being used to model your geometry when you have a CAD model. We use those as a basis to solve the PDEs with. And we don't just do it like this. We have a special trick we pull there, namely we build variational formulations of this IGA basis, such that in one run that is deterministic, now the balloons come again for some reason, in one deterministic run, we are able to predict the response and its derivatives. And by doing that, of course, we now have a very powerful tool in our hands to plug into an optimizer to find the worst and best case realizations of the geometry that minimize or maximize the response that we are looking at. Um, yeah, that's the idea. And so we take out the finite element model, we plug an isogeometric analysis in there, not just any isogeometric analysis, but one that allows to generate variational formulations. If you want to know the hardcore details, I have to refer to this paper. So the article was just accepted with CMAME, I think for the issue of March 2025 it was. If you want, I can also share the paper with you later. Just drop me an email. Um, just a small example in sheet bending, but we did also in the paper a way more cool example that's not monotonic and way more difficult. So this is sheet bending, and that's an engineer. The other example is in the paper. This example that I will show you is about sheet bending, and the issue here is again an engineering issue. So you take a sheet of steel, you bend it in a certain angle, and by doing that, you might introduce damage. This damage that you introduce depends on many factors, one of them being the starting geometry of your sheet. Okay, so what we do to quantify this damage is we calculate a quantity called the stress triaxiality, which is related to the deviatoric and the volumetric strain tensors, or stress tensors rather, that are being predicted by your PDE models. And we want to know essentially worst case and best case, how does my damage in this sheet of metal looks like after it has been um, metal formed. And thanks to our variational formulations that we build of this IGA model, we can also calculate the sensitivity as a byproduct of one deterministic analysis. And so we compare it to a bunch of other methods to calculate the interval bounds. And so you see we can do it in five runs of the full model because we have the gradients for free. Essentially, you break the kind of problem you have with finite differences and optimization over black box models. Of course, the vertex method is still more efficient, but this might be a non-monotonic problem in some cases. So vertex method is not always guaranteed to give you the exact bounds. Especially if you look at the paper there, or I can send it to you, we have like this horseshoe model, which is a complex three-dimensional geometry where it's completely non-monotonic. And there the vertex method underestimates the upper bound and overestimates the lower bound, so it's not conservative at all. And there you see that our gradient-based optimization based on the variational formulation of the IGA model, which does not require you to remesh or anything, gives you the exact bounds in a very limited number of runs. So it's pretty recent work, as you see, 2025 by my PhD student, Nati. Yeah, okay, that brings me already to the conclusions. I realize that I was a bit faster than I planned to be for some reason. So to conclude this talk, if we are doing engineering analysis, we are faced with imprecision. We are not just faced with uncertainty, but we are also faced with the fact that we don't have enough resolution in our observations to model the uncertainty properly. And that means we might not have enough data, we might not have enough knowledge, we might have not enough money to generate everything we need. So in the end, we are looking at a random world through filtered glasses, if you can put it like that. This epistemic uncertainty that we have, the fact that we cannot really see everything the way like we want to see it, gives rise to problems. Namely, we can only bound our reliability levels, and intervals are actually very powerful tools in that context because they are honest. They just say, look, I don't know. I have reasons to believe it's between this bound and that bound. And that gives you then a tool to say something about how sensitive your reliability is with respect to this lack of knowledge that you have. Now, propagating these intervals through reliability analysis is extremely tricky because, of course, you can brute force your way through it, but then you end up with running a global optimization algorithm over a probabilistic analysis, which will cost you forever. So therefore, we have developed a few methods. One was a bit more fun approach based on multi-level Monte Carlos simulation in combination with a Cauchy distribution, which was actually an existing idea that we took and made faster. Another way is to go over the course of surrogate modeling, where we used the Gaussian process regression models and developed some learning functions such that they optimally train for upper and lower bound. And in the special case of geometrical uncertainty, that's a whole different can of worms you can open there if you start changing the geometry over which you are solving your PDEs, because it makes your problems discontinuous and so forth. And there we have developed our isogeometric approach. So that wraps up my presentation. I would like to thank the team, sorry, in Dortmund, and I would be very happy to discuss any and every question you have. In case you have any questions later, or you want to get this copy of the paper that I just mentioned, where we are pretty proud about with the geometrical uncertainties, you can drop me an email here at this address. And also, if you feel like you want to collaborate on any other topic, I'm also always happy to chat. So thank you very much for sticking around on a sunny Friday afternoon, and I look forward to the discussions. Thank you.
And many thanks, Matthias, for a very interesting presentation. And yeah, let's start with the Q&A session. Who wants to start first? Please unmute yourself if you have a question. Otherwise, I'll start. Okay, let me start with the first one. Especially, yeah, where this question came up is when you described the Gaussian process modeling. Where this typically works quite well is if you have data sets for systems that you want to parameterize, where you do not have any specific, let's say, kind of domain bias. Do you have any recommendations how to handle, let's say, something biased measured data or also biased information in general, where, for example, especially in the safety critical domains, you have very scarce data in order to parameterize a model, while you have a huge bunch of data in the domains that are not really critical? How to, let's say, do something against this data mismatch, this imbalance, and also maybe some mitigation strategies?
Okay, that's a very interesting question. Before I try aim at answering it, I first want to make a subtle distinction with the way in which we are using Gaussian process regressions. And so you are right, originally this comes from data-driven methods, so to predict subsurface structures and so on. We use it as a tool to replace the solution of our PDEs. And so we don't have this problem that you mentioned because we can essentially probe our PDE models as much as we want, given by a certain constraint in time. Of course, we want to probe them in the most interesting points, and that's where this work was about, is what are the most interesting points to probe my PDEs, such that the GP model that I train over it is the best one that I can have. I know optimal is a very tricky word to use in this context, but you know what I mean. I'm abusing definitions a bit.
Yeah, but at least the optimal thing is you have a ground truth.
Exactly, exactly. So if you have an infinite number of samples, at least you can show that your GP converges at the full function domain to the PDE solution, given some constraints. Um, your question was with real data, if I understood it well.
Yeah. Yeah, especially when you want to, let's say, model parts of your system representation with the help, for example, of some machine learning technique, maybe
Mhm.
a Gaussian process model, in domains where you're not really sure about the physical behavior.
That's
Could be,
tricky.
for example, yeah, it could be something like, for example, let's say you have attenuation phenomena, uh, some dissipation functions that you want to learn, for example, if you have oscillating structures. And the critical operating conditions are typically the ones that are underrepresented because you either see it really scarcely in your data, or maybe they will even destroy your structure, and therefore you don't have measurements. Is there any way how to, let's say, use your approaches in order to detect maybe those points that are really most critical? For example, to reparameterize safety bounds, to use this either in a
Yes,
constructive manner or to rule out models, maybe even.
I'm inclined to say very voorzichtig, yes, in the sense that, of course, the learning functions still work. So if you have a limit state that you can describe, you can use your data to build this Gaussian process regression model. You can use it in the same way as we do it before. You will have a point of excursion of your limit state, and it will tell you how sure the GP model is. Now, this quantity that tells you how sure your GP model is, you can use to evaluate. I don't know why those balloons come all the time. You can use it to evaluate whether or not you trust this response point, and that can be a decision to say, okay, I need to gather data here. Sorry, but we need to destroy the structure to be sure that when this thing comes by, it doesn't destroy the structure. But at least we can predict it next time. That's my intuit. It's I pull it out of my ear, of course.
Yeah. Hmm? Yep.
But I can see that possible. Yes.
Yep. Okay. And the second question that I had, this is more or less related. If you go back this couple of slides where I had this bending example, I forgot the slide number. Yeah, this one here. What you assumed, but maybe please correct me if I misunderstood it. You assumed you know the geometry already, and the geometry had some uncertainty. And this was represented then in order to perform afterwards the analysis. Uh, do, do you also use your techniques in order to optimize the geometry, the structure, in order to get something where you're preventing, for example, the risk of a crack or material destruction?
We didn't do that yet, but it is indeed the same machinery, because we are now looking for the worst, and so we know. You said we know the geometry, and I maybe skipped a bit too fast over the explanation of how we model the geometry in the first place. So you have these NURBS models, and we put intervals on the parameters of these NURBS. So we can actually have very high flexibility on how that geometry looks like. But now the problem of finding the worst and the best case behavior, given the fact that you have bounds on this knowledge, or is the same problem in a way as finding the best possible geometry aimed at minimizing a certain response.
Mhm.
It's a small reformulation of the
Yeah.
optimization problem, but in the end, the machinery is exactly the same.
Okay. Thanks a lot. I've seen that Katja has unmuted herself. Katja, do you have a question?
Yes, I have one, but I'm not sure if you can hear me.
Yeah, it's
Yes.
working perfectly.
Okay, all right. So thank you. Thank you very much for your talk. I just wanted to ask about the same slide, actually, or the same general topic. So I'm not sure if you know the works of Professor Neil Stewart, who worked for a lot, well, for a long time actually on those nerves in the context of uncertain geometrical modeling. So my question was, do you know about him and what is the difference maybe in your two approaches?
I have to admit that I'm not aware of those works, so I would be extremely interested in reading them.
All right. Okay, thank you.
Yeah, thank you very much for the suggestion.
Uh,
Can you maybe drop the name in the chat or something that I can tell my student also to look at it?
I will write you. Yes, yes, I will.
Thank you.
And my next question is, so in the conclusions, you told us that, well, propagating intervals through black box models is tricky. That's correct, and I absolutely agree. But when you say tricky, it sounds like, well, you know how to do this, at least in a couple of cases. And that's why I'm asking, so you know how to propagate intervals deterministically through black box models, or what do you mean by that? Can you do this without stochastic models, without
Um,
two?
yes, yes. So there are a bunch of ways in there. So the most intrusive one would be to replace all your arithmetic with interval arithmetic, where you
Yes, yes,
end up with the risk of blowing up.
yes,
So
but
there are
this
these.
wouldn't be black box
That's
model.
not black box. No, no, indeed. So
I'm interested in black box. So can you do this in black box models without stochastics?
you can, I think the only way in which you can attempt is to use global optimizer. But then, of course, it depends on whether you can have some convexity. Then you don't need a global optimizer. So optimization would be one way that comes to mind. That's how we do it, at least. If we have a pure black box where we have no idea what's inside and we cannot do anything else, the safest option is to hit it with a global optimizer. That's in the end what we do with these Gaussian process models also. Of course, there you have the problems of proving that you have the exact bounds, which is, I think, correct me if I'm wrong, still an open question
Yes, of course.
for a
Yes.
general non-convex model. So we try to limit and usually also the extent to which the response space can move as such that at least you can assume moderate certainty, some convexity, and so on. I don't know if that's a satisfactory answer to your question.
I understand now what you mean by that. Thank you very
Okay.
much.
So the issue becomes, of course, if you put a stochastic model in the middle, that for every realization of your interval, even though if you give it the same realization, it might give you a different number at the output. And that creates a whole nightmare because for your opti, that's what I meant with tricky. I realize that my wording is sometimes maybe a bit too imprecise. Uh,
Okay, do we have any further questions? I have a last philosophical one.
I love those.
Uh, yeah, and the reason is if you have students, let's say bachelor students, master students, they definitely take, let's say, practically all the things. They're doing simulations, they're doing maybe also an analysis of some textbooks example. They take everything for granted. They assume that everything is known precisely and that things like uncertainty really doesn't exist. Your talk, in fact, is the absolute counterpart. What you described. You described a
Yes.
complete bunch of aleatoric uncertainty, epistemic uncertainty, maybe even partially talked about existential uncertainty. Now, what would your suggestion be? How to advocate for the use of suitable tools for modeling uncertainty already in early stages of a study program? That's one thing. And how to advocate for the same thing also in industry.
I can answer from front to back. So you mentioned this problem with students. It's not only students. So I have had talks with companies, big companies, who say variations on the following theme. We have good measurement systems, therefore we don't have uncertainty. So I agree with you, it's a very widespread misconception. How would I advocate for bringing it in there? In the end, in my opinion, taking uncertainties into account is proper engineering. It's just being honest. It's acknowledging that what you don't know. I mean, forgetting about uncertainty doesn't make it go away, right? I mean, assuming that everything is deterministic doesn't make it deterministic. So that's, I mean, I seem to be lucky with my colleagues that they agree with me that uncertainties are important for our students. But in the end, you can never know. So what I usually try to do is do it case by case. For instance, if I have a good collaboration with the people who are doing metal forming, and they know that perfectly well. If you talk about friction coefficients in a strang press machine, how is it called? Hot extrusion press.
Mhm.
They also say it depends on almost everything. So that means you cannot quantify it unless you measure it perfectly. If you buy plates of steel from a different manufacturer, you have different properties. So my answer to your question now is would try to make it as precise as possible because the risk of this topic is that you can get lost in aleatory epistemic existential philosophizing about where the boundary is between all of them. But in the end, you have to solve engineering problems, or at least we have to solve engineering problems. So the best way to convince people that the problems are real is to showcase it. So my first lecture on reliability engineering, I spent half a class showing examples where well-meaning people underestimated the uncertainties and bad things happened in the end. Um, so for engineers, we understand the language still, the language that we understand the best still is to show what it means and what the implications are.
Yeah, I think those are almost perfect closing words. And yeah, I think definitely we all of us yeah, have to show the people with whom we are working together that uncertainty is really a crucial thing in reality. And yeah, also especially those people who just believe in data science, who just plug all the data somewhere in some databases, data lakes, or whatever, without annotating them with the respective quality that the corresponding data have. I think this is really something all of us should keep in mind. And yeah, this will
Thank
also bring research forward. Many thanks again, Matthias, for your presentation.
thank you very much for inviting me. So if I can use the last 1 minute to shamelessly promote the REC that we will organize next year in Dortmund. So if you, I guess we are all interested in uncertainties, otherwise we wouldn't be here in this meeting. So if you don't have any plans yet in September next year, and the estimate is still imprecise, so I will make it more precise. I'm talking about September, I think 2 to 6, but I want to be more precise. So if you don't have any plans yet, 2 to 5 September 2026, you are very warmly welcomed in Dortmund. We will be organizing the biannually REC conference that was last time in Beijing. We will organize it in Dortmund. The website is online already, or if it's not, it will be online very soon. And I think, yeah, it will be nice, it will be fun, it will be interesting. So you're all very welcome.
Yeah, again, many thanks. And yeah, now the only remaining thing is have a nice sunny Friday afternoon.
Yes.
And yeah, let's see each other again very soon in the next online seminar.
Thank you very much. See you all. Thank you also for the link.